This video will cover the second part of Section 2 and cover parts of Section 3 from Chapter 14. We'll discuss how to determine whether the regression model and the slope coefficients are significant. We'll also talk about how to use the estimated regression equation to make predictions. When we're doing simple linear regression, there are three tests that are statistically equivalent. The test for significance of the correlation between x and y, that's what we covered in Section 14.1. The test for the significance of the coefficient of determination, the test for the significance of the regression slope coefficient. These tests are all equivalent in the case of simple linear regression where we have only one x variable. In the case where we have more than one x variable, this test of the r-squared and the tests for the betas are no longer equivalent to the correlation test. So to test for the significance of the coefficient of determination, or really to test if the model is statistically significant, we will do a hypothesis test where the null is that the r-squared is equal to 0, meaning the independent variable does not explain a significant portion of the variation in the y variable. And the alternative hypothesis will be that the r-squared is something other than 0, and that the independent variable does explain a significant portion of the variation in y. The test statistic for this looks very much like our test statistic for ANOVA. It's an F-score, and the F-score is the sum of squared regression divided by the degrees of freedom for how many variables we have. In a simple linear regression, we only have one variable, divided by the sum of squares error, divided by the number of degrees of freedom associated with that, which is the number of items in the sample minus however many x variables we have minus 1. In this case, we have one x variable because we're doing a simple linear model, minus 1. So n minus 2 really. Excel and Minitab do this calculation for us. They use numbers from the ANOVA block to calculate the F-score. So the sum of squared regression is 18,934 divided by 1. The sum of squared error is 13,665.57 divided by 10 minus 2 for our example when we were using square feet as it impacts the price of housing. Our F-score is 11.085. We use that F-score and we compare it to an F-critical, which can be found in the table or using F inverse in Excel. So if our alpha is 0.05, our D1 is 1, and our D2 is 8 degrees of freedom, our F critical value is 5.318. Since our F score is greater than our F critical, we are able to reject the null hypothesis. What that means for us is that the model is statistically significant in explaining housing prices. Our square feet really does matter. Before we can talk about hypothesis tests for the individual beta, we need to talk about some estimates of spread. So you'll see something called the standard error in the output from Excel and Minitab. This standard error of the model is the variation of the observations around the regression line. We denote that S sub E, standard error, and it's really just the square root of that sum of squares error divided by the associated degrees of freedom. This is going to tell us about how far off our estimate could be expected to be from the regression line, from the predicted value we get from a regression equation. The standard error for an individual regression coefficient is actually estimated using that standard error from the model. So the standard error for our slope coefficient is the standard error of the model divided by the square root of the squared deviations of x around its mean. These standard errors are estimated for us using the softwares. The standard error for the model is 41.33032. Because we're talking about housing prices, and this is in dollars, we're really talking about our model being off by about $41,330 on average as we make estimates using the model. Our standard error for our slope coefficient is 0.03297. So that tells us that we can expect this coefficient to be off by about 0.03297. Since this is in dollars, we know that our estimates when we talk about that slope coefficient are probably off around $33 in either direction. So focusing on the left column, what we see is the variation in the observed values of y from the regression line. If our standard error of the model is very small, the dots will be really close to the line. And we usually compare the standard error to the mean of the y variable to know whether it's small. When we have a small standard error, the model accurately or relatively accurately predicts what's going to happen with y. When there's a large standard error, and when we say large, we mean the standard error is big compared to the y, then that model doesn't predict as well what's going to happen to y. Notice the dots aren't very close to the line. So when we make a prediction, it will be on the line, but the actual value could be quite a distance away from the line. When our standard error of the slope coefficient is small, then we have a range of lines that look fairly close to each other that could probably be true. When that standard error is large, we actually don't know what the slope of that regression line looks like, and we could even have a positive estimate, but with a large standard error, the true line might have a negative slope. So now that we know about standard error, we can do a hypothesis test for that slope coefficient. To do the hypothesis test, what we're really trying to say is there a linear relationship between the x and the y variable? We're really trying to do a test about the beta that was out in front of the x variable. So our null hypothesis will be that beta 1 is 0. What that means is that there's no relationship between the x and y. If we plug different values in for x and we multiply that by 0, y will not change. There's no linear relationship. If the beta 1 is shown to be something other than 0, there is a linear relationship between x and y, and as we change the values of x, we get different values for y. The test statistic looks much like the test statistics we've used in the past. We take our observed value from our sample, so this will be the slope coefficient that we get in the regression model, minus the hypothesized value for that population parameter, divided by the standard error for that slope. Because we have to estimate two values, our degrees of freedom are n minus 2. Let's go back to our housing prices and square feet example. We had our estimated regression equation. House price with the hat on it, that tells us this is the predicted equation, is 98.25 plus 0.1098 times square feet. What we're trying to do with this kind of test, this hypothesis test of the slope, is to determine if this 0.1098 is statistically different from 0. So the question is, does square feet actually impact the house price? This piece is copied right out of the Excel output. Minitab also provides us this output. We're going to look at the row that says square feet because we're trying to make an inference on this coefficient associated with square feet. Our B1, or our estimate of beta 1, is this 0.10977. The standard error is given here, 0.03297, but our t-score is already calculated for us, so we don't actually have to do the work. Excel has already taken B1 minus 0 and divided that by the standard error to get our t-statistic, or our t-score, of 3.329. So we have this 3.329, we need to compare it to a critical value. We use t.inv.2t. We have 5% of the area in the two tails, so as we plug that into Excel, we put 0.05 in for our probability, and we have 10 minus 2 degrees of freedom. There are 10 observations minus the 2 things that we have to estimate. That gives us 8 degrees of freedom. The critical value then is 2.3060. Our t-score is in the rejection region, so there is sufficient evidence to say that square feet affects house prices. We could also use the p-value approach to answer that same question. The p-value is 0.01039. Since our p-value is less than alpha, we can reject the null hypothesis and accept the alternative. When we accept the alternative, we say that square feet does impact the price of a home. In part 3 of chapter 14, there are several things that we're going to talk about. The first of these being the confidence interval estimate for the slope coefficient. The calculation is really that sample statistic that we get, or our point estimate, plus or minus a t-critical times the standard error. So this is the same general form that we've used before. We are just now using values that are specific to our coefficient in this regression equation. Excel also calculates for us automatically the 95% confidence interval. We can ask it to generate a different confidence interval for us if we're interested. Minitab will do the same thing. What that tells us is that we're 95% confident that the average impact on the sales price is between $33.74 and $185.80. One of the things you can do with this is also test that same hypothesis. Note that 0 is not inside the confidence interval. Since 0 is not inside the confidence interval, we can reject the null and accept the alternative that square feet impacts housing prices. Another thing we can do with regression is make predictions. So we might want to use this regression equation to try to tell a client that comes into our real estate agency what they should charge for their house. Suppose that the person comes in and they've got a 2,000 square foot home. We want to give them a starting price to list their house at. All we do to provide them with this estimate is take that 2,000 and plug it in where we've got square feet, because that's our variable. So 2,000 times 0.1098 plus our intercept tells us that the house should be priced at about $317,850. There are some problems with regression. When we use regression to make prediction, we can often be quite wrong, especially if we have a large standard error for the model or a large standard error for our individual slope coefficients. We also have to be careful because correlation does not imply causation. So just because the two variables are correlated to each other and we can run a regression on them, that does not mean a change in x causes a change in y. Also, just because an r-squared is big, that does not mean our model will be a good predictor. R-squared simply means that the line fits really well to the sample data. So we can use regression to talk about the change in x as it affects y and to make predictions, but we have to be cautious about how certain we are in those results.